Today is the 24th. We already worked on the scalar product, which was the cross product. We looked at the definition. We looked at the properties, 6 of them. Where when the sixth, we said that when the that product equals to 0, it means that the two vectors are perpendicular to each other. So we can move on and say that, or do an example for that matter, just to see how these play about. And the example is that if the vector A equals to 2y plus 3j minus 5k and the vector B is equal to 4i minus j plus 2k their scalar product is given by A dash B. Please, if you are not registered on the machine, don't try it. If you are registered, make it read your finger. Put the finger flat in the place and try to recall how you did it in my office. But what you do shows who you are anyway. Forgetful, careless, and unprincipled. So A that B would be the same as 2i plus 3j minus 5k divided with 4i plus minus j plus plus I think this should be 2 here plus 2k for consistency. So I'm daring the 2, so if I'm daring, I multiply the magnitudes. So this would be the same as multiplying, of course, I dot I, you get a 1, but when you get I dot j, then they become perpendicular, so will be I dot k. Be perpendicular, and then you will get a 0. So this would be this would go in the 3 of them, but as it goes in the 3 of them, it is only the I that survives. The I dot j is 1 times 1, and then the angle between them is 90, and the cosine of 90 is 0. So we're going to get 2 by 4. Then we have the I dot I surviving. We add on 3 by negative 1. The j dot j survives. This is plus minus 5 times 2. The k dot k survives. The K dot I, K dot J all die out because of the angle between them being 90 and giving us 0. This will be 8 times the 1 plus 3, which is negative 3 times the 1, then plus the minus 10 times the 1 that results in that. And then we have this being the same as 8 minus 3 minus 10, which is equal to 5 minus 10. You can apply my dogs as small or body mass, whatever you want. This would be the same as minus. Therefore, our A that B in the example is equal to that. And as you can see, we got no either I, J, or K. So indeed, cross product of any two vectors, I mean dot product or scalar product, scalar or dot product of any two vectors results in a scalar. I did all this just to give you an impression of how it should be. And I didn't want to assume that you all know how this is done. Fortunately, all of you have done this in high school. But as it is a case, you only did it to get an A and come to Makerere. The next part is the vector product, or which we call the cross product. So the cross product, sometimes which we call the vector product of any two vectors A and B, is given by A. So as I told you that I'm happy to get the a vector being a half-headed arrow. I remembered what I said last time. So I'm looking at imbalance. Look for where to go, the last one. Or swap with the Selwaji. Swap with them and the Holy Spirit will protect you. But when you swap still, there will be an imbalance. So try to make sure that she can go up, he comes down. That's how I do it. And the last lecture which we had on the top is on YouTube already. So if you want to see what I said or whatever, no editing. It's called verbatim. The way it was is the way I put it. So the cross product can be given as A cross B, which you are used to. But I prefer writing it as A inverted B. This is how I will be denoting my cross product. So the nomenclature for my cross product is A inverted B, B. So it's given by A cross B equaling to the magnitude of vector A times the magnitude of vector B, then the sign of the angle between them, which can be just written as A, B, sine theta. That is for if the two vectors are oriented to each other as shown below. So we have, if this is our vector B, this is our vector A, and the angle between them is theta. The definition of the cross product is as that. And of course, we said that where the angle theta is between 0 and pi. We have a couple of rules. We want to see whether it is this product is commutative, whether the result of the cross product is a vector. Hence, the reason it is called it's called a vector product. The notes I'm giving are just a guide. The detailed notes are on where they are too detailed. Here I just make you flow with me during class to have something to work with. So the following are laws valid for a vector product or a cross product. And these laws are that when we look at the commutative, we say that the A then B is equal to B dot A. That this one doesn't hold at all for this product here. So we shall have that one A cross B is equal to minus B cross A. Once you know the laws, life becomes very easy. So not commutative. It's not commutative. The next one was, if you have now the three vectors and you try to cross them, cross one, the sum of them. So C cross B. Should we start with the C, or I can say A cross B plus C. Just for consistency with regard to that product we had last time. This would be the same as A cross B plus A cross C. And indeed, we say that it can be distributed across. So this is distributive law. 3 is that if we had a scalar and that scalar is multiplied across the cross product of these two vectors A cross B, this would be the same as scalar then A cross B plus, not plus, similar to vector A crossed with the scalar multiplied with B, or you can rewrite it as A cross B, and you can multiply the scalar on the other side. Doesn't matter where you multiply the scalar across. After all, it will affect the whole product at the end of the day. 4, if we consider the unit vectors I, J, K, then we shall say that if we cross the two vectors, I cross I, J cross J, K cross K, the angle between them is 0, 0, 0, and the sign of 0 is 0. So I cross I is equal to J cross J is equal to K cross K, which is equal to 0. Because according to the right hand rule, this being our K, this being our J, this being our I, the angle between them is all 90. And the angle between each of the individual vectors II, JJ, KK is 0. And the sign, according to the definition, the angle between them, when it is 0, according to the sine wave, this being 1, this being -1, pi over 2, 0, pi, 2 pi over 2, 2 pi AC. We find out that the angle 0 gives us sine 0 being 0. However, when you cross the two consecutive unit vectors, you get the next in this. So if I cross I and J, and you have to go in an anti-clockwise direction, is that true? So if I get IJ, I get a K, so IJ gives me a K, JK gives me an I, KI gives me a J if you flow in an anti-clockwise. So and I cross J gives a K, J cross K gives an I, and then K cross I gives what would happen for the JI? It's also JI, according to the commutative law, JI gives a minus K, KJ gives a minus I, IK gives a minus J. If we got our two vectors A and B expressed in terms of the unit vectors, then we can cross them up and use the method of determinant to find out the cross product. So if our vector A, that would be our 5. If A is equal to AX I plus AYJ plus AZ K. And where is my machine? Please, I use it as a clock. So it's my clock. If you have it, please, and everyone is done, you bring it here so that I know what time is. And B is given by BXI plus BYJ plus BZK. Then our A plus B would be given by the determinant of we got our I, we got our J, we got our K, and then we list our components of A along the I, J, K, and the components of B along the I, J, and K. So I got our AX, AY, AZ, DX, DY, DZ. And to find the determinant, we use the determinant method where you say if this is a plus, this will be a minus, plus. Depending on your matrix, you keep doing that. Plus, minus, plus, minus, plus, minus. We got on a 3 by 2 matrix, so you got our plus, minus, plus. If we are looking for the I component, then we must make sure that our A cross B will be equal to, so I will shadow out the I. And when I shadow it out, take the determinant and I'll give it an I. If I'm going to the J, it means now I'm going to shadow out this, but it will acquire a negative. And when I'm looking for the Z, I shadow out this. After cutting it off, I do the determinant, which is left minus right, and then I get a result. So I'm going to have the I cover all this, left minus right. So I got our A, Y, B, Z, minus B, Y, A, Z. That is our I. I shadow out, I put it out this. And I get it A is AY, B, Z. Then I subtract the BY, AZ. And then instead of adding, this rule of determinants gives me a negative. So minus, I cut out this, and then I get our left minus right. So I will have AX, BZ, minus DX, AZ. And I get as the J component. Lastly, I cover the K to get the K. If they are discussing about you and you have a case, to avoid bias, if you are a strong man, they send you out, isn't it? They were following the principle of cross product. So if you are guilty, if you are a suspected failure, they say stand down. And when they say stand down, they mean that they just want to make sure that your influence is not part of the problem. So because if you are too strong, you may be there and scare them out. So that's why we cover up the thing that we are looking for. So this will be class. I cut out this, get the left AX, BY, minus DX, A, and this gives me the K compound. And that's how we get the cross product. If the cross product is 0, if the cross product A cross B is equal to 0, it means that the two vectors are along the same direction. Then A and B are parallel. Those are the couple of the rules, and other products can be formed in a similar manner. So you can do a couple of stuff using these simple rules. But these are the key rules that once you know them, the other bits become very simple. When we have speed, we differentiate. I mean, when we have distance, if we know how the distance has been varying, we can differentiate it and get the velocity. If you have the velocity, whereby one only separates speed and velocity, and I mean, speed and velocity is simply that velocity is interested in the direction in which a body is moving to, whereas the speed is just how much it is moving or how fast it is moving. So when we have a distance, we can get the velocity by doing what we call differentiation. We can differentiate the velocity to get the acceleration. On the other hand, if you are already given the acceleration, you can do it backwards and instead move from integration and do the differentiation. So on that note, we need to know how we do the differentiation of vectors. So derivatives of vectors. So the vectors can be split into components, and in this case, they may be thought of as functions of the components of A. Therefore, depend on some scalar quantity, say x. So if we, for example, if the vector A is given by A is equal to AX, how should I separate? A equals to, if it is along the X, that means I'll be having this equal to along the I. Is that okay with you? Does that make sense to you? Okay, so if it doesn't make sense, I can still maintain it as a vector. If you don't want to see scalar A along the I because it is a function of X, you can still mention it as a vector A and then along the X. We can do the differentiation. Who remembers the definition of differentiation from locally class 1? What would be the dA dx? dA dx would equal to the limit as dx tends to 0, ax plus dx minus ax over dx. Just a definition. And provided the limit, exists. If we had our example of A being, if our vector A and as a vector, assuming it was varying with the position R, where R is xi plus yj plus zk, was equal to A1 I, should I say A1, or I can use A1 xi, because I don't want you to find me later. So A1 being a component, I need to put that, then A2, we are using the x above, so I will still use AX. So the x really is not the x, y, z you are used to. But if we had followed this I, j, k, and take an example of what we have here, then I would rather say that this is A1x, this is AY, plus A3, Z, K. If I have this vector where R is equal to XI plus YJ plus ZK, then the differentiation, not differentiation, the derivative would be the same as if you differentiated each of them individually. So that means if I differentiate this individually, I will get a dA. So this would be dAr, dr, being the same as dA1x dx I plus dA2y dy j plus dA3 z dz, and this should be along the k. We can do an example just to have a feel of how this goes about. So if our A is 2r squared minus 3r, if our A is equal to 2r squared minus 3r I plus 5 cos r j minus 3 sin r k, then we can find the derivative of this by looking at the derivative of each of the components of this vector. But fortunately, all of them, so our dA, dr, we shall individually differentiate each, so this would be dr of 2r squared minus 3r along the I plus dr of 5 cos r along the j minus dr 3 sin r along the k. And we can do this, that this would be, we subtract the 1 from the index and multiply by the new index. So this, multiply by the index, then take away 1. So this would be 4r minus 3i plus When we differentiate a cost, we get minus a sign. So this is minus 5 sin R along the J plus 3 cos R along the K. Oh, there is a minus here, so we get a minus. Therefore, dA dr is equal to 4R minus 3 minus 5 sin R J minus 3 cos R yes.
Here, the A to the AR to the vector. As I write A, it's a very trying to put another meaning that A is a function of X and A is a function of Y. Here, this vector we are put as if A, the vector AR.
This one.
Equals to A1 X. And try to do that A1 is the function of X, A2 is the function of Y, A3 is the function of
yes.
But the main vector is the function of R.
Yes, and that's why I said this R here is a position vector. And that position vector within a given space, that position vector R can be given by I, J and K, depending on how much they are from the given position. I mean the origin. So if I am to describe this fan and I'm having an origin in this corner, it will be a different position if I'm describing this fan. And according to the Z, J, or K, J and I. So the position of the fan is dependent on how far you are, how far you're going to move along either here. So either I'll first move around here, go directly to it, and then I count how much I move, and then move along the J, go below it, and move a couple of K and reach it. So my movement will be described as moving from the origin here. I walk a couple of steps until when I reach almost towards it, but they tell me move a couple of them, then I reach below it, then I move and reach it. So my movement will be described by these three compounds. This example shows that the rules of differentiation in calculus can be extended to the vectors, and these rules include partial differentiation. For example, if we had two vectors B and A, for example, if we had A and B, and we want to do the partial, we can look at each of them partially and then eventually come together. Or if you had a scalar of 1, then you can do the differentiation according to the scalar. Do I have to do that also? See partial differentiation part. Oh, well, if I do that, I won't earn my money comfortably. Some will say, left some parts, so you shouldn't be paid. As if you have that chance. The rules of calculus on differentiation can also be applied. In the depreciation of vectors. So if we had a vector, like phi and A, let's consider vectors AR and BR. Then we can, if we DDR of A, R, BR will be the same as, remember how we do the product? We get VD UD plus UD VD. And so if our U is there, our V is here, then this would be our V, the AR, the R plus AR, the BR, the R. Those rules apply in the same sense. If you have A cross B, you do the same stuff, so you get more from the notes in order for me to cover as much as possible for today. As I said when I was trying to work on this, I said that if I have a distance x, and I look at a given time which this distance was moved, then I can calculate how this distance, how speedy or how fast this distance was covered. And that's when I say that I can say speed is equal to dx dt, because I know the distance that was covered, I know the time in which it was covered, I can know how fast it was. Similarly, if I know how fast the body was, actually I can get to know how much the body moved or how long the body moved if I know how much time it took for the motion to take place. And I can do that by having an idea about the integration of vectors. Don't mind about my pronunciation, mind about what I'm talking about. So the integral of an acceleration gives you a velocity. Integral of the velocity gives you. So if we have the consider a vector function AR, consider a vector function AR, and if I have such a vector function AR, I can find out, or I can first split it up and say where this AR is equal to A1 as a function of R, I plus A2, R, J plus A3. Do you prefer me saying R or I use the X, Y, Z? I don't know what you prefer. I'm just taking A being a function of R, so I'm not bothered about whether R is just like an X or a Y or a Z. And like when I had a position vector, a vector being a function of a position of a given point. So this would be K. Then I can find the integral with respect to R, and this would be then the integral, where integral is a snake, a red striped snake. Some of you who have ever seen such a thing. This is how we draw an integral, but the integral is actually a stretching. When you are summing up discrete values or discrete variables, where you can't really make them continuous, when you try to look at them in a form of continuity, then you try to stretch your discrete things. So when you stretch this, it doesn't really become straight, so it just stretches a little bit and becomes an integral. So the integral A R dr will be integrating each individual component. So this will be integral A1R, dr plus. Do you prefer putting the vector inside or putting the vector outside? Outside, so we can do our business first. Then integral A2R drj plus integral A3R dr. Okay. If there exists another vector BR such that you have the A being the differential of BR, the way you used to say it's a differential of the, remember that part of the integration where you first, I used to like mathematics, especially in A level, where up to now I wonder, you look at a value and they're like integration by inspection. You look at it and inspect and say, this should be this. It used to make me really look at mathematicians as smart people, They look at something and they will tell you, I can use separation of variables. And then they look at, they say, the denominator is a function of, is a derivative of the function. So I will use, I don't remember very well. Okay, C notes for the other part. This is taking so long as I didn't expect. So examples are that we look at velocity being like differentiation, acceleration being the differentiation of velocity. Velocity, and then you get acceleration. So I would still say that C for the other parts and examples where an example is velocity and acceleration. I just wanted to go through this, otherwise I would have said that you go and look at vector calculus, which is applicable to our course, but I wanted to make you look at vectors in another dimension. That's why I did all that part. Those of you who have been on Mwere, you'll be able to see that actually everything is orderly, and where you get a problem, I'll be able to work on it. In electricity and magnetism, you find a couple of vector operations. And these vector operations, one of them, whether you are doing mathematics or whether you are doing physics, doesn't matter. You will have to teach math and physics for those of you who are math major. So there is what we call, under this, differentiation and integration introduces some operations which are going to be, for example, the gradient. So when we talk of the gradient operator under this part, the gradient operator del which we use the del. This is denoted by the symbol invalid change, small change, capital small change, and we have it as this. So this del operator is the symbol. This is del operator, and is given by, which is given by del equal to Kali by Kali x I, Kali by Kali x I plus Kali by Kali y j plus Kali by Kali z k. And this is for when we have our vectors for the Cartesian coordinates. So you'll find that this del operator can be either dotted with a vector or can be crossed with a vector. So when we cross it with a vector, we talk of the curl of the vector. When we dot it with a vector, we talk of the divergence. So if I got any vector A, and I take the del operator, and then I dot it with that vector A, then I can simply say the divergence of A. If I get this vector, take the curl of the vector with the vector A, and then here I say the curl of, and at the back of the mind, you have to make sure that you know that the del operator is the same as Kali by Kali xi plus Kali by Kali yj plus Kali by Kali zk. So 2, we look at the divergence. So the divergence of any vector, we define it as the dot product between the gradient operator and the vector. So the divergence of a vector is the dot product. In brackets, we say the dot product is the scalar product of a vector of the gradient operator and such a vector. For that matter, we say that if we got a vector, if the vector A is given by A is equal to, what do you want to use, AX or AY? So assuming it is AXI plus AYJ plus AZK, and then the divergence of A would be equal to Kali by Kali xi plus Kali by Kali yj plus Kali by Kali zk dotted with AXI plus AYJ plus AZK. So it means we're going to have the Kali AX by Kali X I plus Kali AY by Kali YJ plus Kali AZ by Kali Z K. And then this would be our divergence. The next part would be the
the final product they have answered. You don't expect it to have the same because they say that.
Yeah, I think you are very right. So if we had the dot, this shouldn't be there. Remind me at the end, I'll add you one mark, in your marks. You are precious or what? Yeah, I know. Somewhere. So the divergence operation gives a scalar. The divergence operation gives a scalar result. Finally, for today, I want to look at the curl. 3 is the curl of a vector. And the curl of a vector is a cross product between, this is the cross product between the Brownian operator and the vector. So the curl of the vector is the cross product between the the Brownian operator and the vector. So the curl for a vector A equaling to AXI plus AYJ plus AZK. The curl cross product between A and the Brownian operator would be along the I, J, K. I start with the components of the del operator, Kali by Kali X, Kali by Kali Y, Kali by Kali Z. I have AX, AY, AZ, plus minus plus, such that our curl of A is equal to take away this, so I have Kali AZ by Kali Y minus Kali Y by Kali Z along the I subtract Kali Y, Kali X minus Kali X, Kali Y, J plus Kali AYX, then minus Kali X, Kali Y, Kali X by Kali Y. This would be our K. And the cross product, the curl of a vector has a vector result. The curl of a vector has a vector result. In your free time, you're going to have to complete this by looking at the fourth part. And the fourth part is about the line integral. The line integral. This is your HW, homework, hostel work, homework. So I guess the H is appropriate for wherever you stay. Anyone, when you stay in Namasiko, I'll take it as a homework. And there is a summary that the quantities of physics are either scalar while others are vectors. Both scalars and vectors can be treated with the rules of calculus. Position, of course, then particles of positions of given particles which vary with the time may have their velocities and acceleration reduced as vectors, and various vector operations result into gradient, divergence curve, and line integral. Okay.